Good afternoon. Welcome back, everyone. I'm Steve,
And I'm Scott.
broadcasting from Apple Valley, People's Republic of California.
Yeah, and we're talking about another science topic, quantum secrets. But we haven't mentioned this. We don't mention this enough, and I don't think we mentioned it lately. But we really appreciate the people that have subscribed and that listen, and that are regulars and tuning in. Really appreciate it.
We like the comments.
Yeah, we love the comments, and we hope you're getting something out of this because
We are.
yeah. 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 Okay, here we go.
Okay, here we go. Cambridge scientists have uncovered a hidden quantum mechanism in an organic semiconductor. You heard that right, organic semiconductor that could revolutionize solar energy. In a finding that connects modern research with ideas from a century ago, scientists have identified in an organic semiconductor a behavior that was long believed to occur only in inorganic metal oxides. The team, led by the University of Cambridge, reports a previously unrecognized way to convert light into electrical energy. I wonder if they're talking about what are those light bugs? The light, what are those? The
Lightning, the
fireflies.
firefly.
I wonder if they're talking about that.
We just talked about that, right?
I know we did. Spiders.
The spiders.
Spiders. Okay. This advance could reshape solar power and electronics by enabling lighter, cheaper, and simpler solar panels built from a single material. Would you like to know more?
Okay, the research centers on a spin radical organic semiconductor called P3TTM. That's Tom, Mary. A single unpaired electron sits at its core and gives the molecule distinctive magnetic and electronic properties. The project combines the synthetic chemistry group of Professor Hugo Bornstein in the Youssef Hamid Department of Chemistry with the semiconductor physics group led by Professor Sir Richard Friend in the Department of Physics. Okay.
I deployed with a guy stationed at Abu Ghraib for construction, and he was Sergeant Friend, and that was a weird name. I thought I'd never see that name again.
Was he a sir?
No. They have developed this class of molecules to give very efficient luminescence as exploited in organic LEDs. But the new study published in Nature Materials on September 30th, 2025 reveals their hidden talent. When brought into close contact, their unpaired electrons interact in a manner strikingly similar to a Mott-Hubbard insulator. A thin film emits red light from radical doublet excited state.
Wow. Your cat likes it. Your cat. Quote, "This is the real magic," explained Bywin Lai, the lead researcher at the Cavendish Laboratory. Going on with the quote, "In most organic materials, electrons are paired up and don't interact with their neighbors. But in our system, when the molecules pack together, the interaction between the unpaired electrons on neighboring sites encourages them to align themselves alternately, up and down, a hallmark of the Mott-Hubbard behavior. Upon absorbing the light, one of these electrons hops onto its nearest neighbor, creating positive and negative charges, which can be extracted to give a photocurrent, which is electricity."
Well, I understand everything they're saying, but I'm trying to picture it. So the team demonstrated this by creating a solar cell from a P3TTM film. When light hit the device, it achieved a remarkable close to unity charge collection efficiency, meaning almost every photon of light was converted into a usable electrical charge. That's awesome. In conventional molecular semiconductor solar cells, the conversion of an absorbed photon into electrons and holes, electricity, can only happen at the interface between two different materials where one acts as an electron donor and the other acts as an electron acceptor, and this compromises overall efficiency.
So you understand it, but you don't picture it. Well, I picture it, but I don't understand a word of it. So, in contrast, for these new materials, after a photon is absorbed, it is energetically downhill to move an electron from one molecule to an identical neighboring molecule, thus creating electrical charges. The energy required for this, often termed the Hubbard U, is the electrostatic charging energy for double electron occupancy of the molecule that has become negatively charged.
Dr. Petri Murto and the Yusuf Hamid Department of Chemistry developed molecular structures that allow tuning of the molecule to molecule contact and the energy balance governed by Mott-Hubbard physics needed to achieve charge separation. This breakthrough means that it might be possible to fabricate solar cells from a single, low-cost, lightweight material.
The discovery carries profound historical significance. The paper's senior author, Professor Sir Richard Friend, who we refer to above, interacted with Sir Neville Mott early in his career. This finding emerges in the same year as the 120th anniversary of Mott's birth, paying a fitting tribute to the legendary physicist whose work on electron interactions in disordered systems laid the groundwork for modern condensed matter physics. Okay.
Let's watch this closely, Scott, and see where it goes. If it could revolutionize solar, that's great. I personally like the idea of like decaying radioactive, that's luminescent, and it can charge cells from that. I like that idea. Little dab will do you on each cell.
Okay.
All right, folks, you heard it here. Okay. Thank you for joining us. We'll catch you tomorrow.
Take care, everyone. You have a good night, and we'll see you tomorrow.